All right, one more example here. We have a merry-go-round again. It has a rotational inertia of 880 kilogram meters squared. It is rotating at 20 RPM. John runs tangent to the merry-go-round at 5 meters per second in the same direction that it is turning and jumps onto the outer edge. John's mass is 30 kilograms. What is the merry-go-round's angular velocity in RPM after John jumps on? Treat John as a point mass. All right, so I'm going to make the merry-go-round object 1. This is a collision. John was not on the merry-go-round, he jumps on, so this would fall in the category of a collision. We can say the radius of object 1, the merry-go-round, is 1.5 meters. The rotational inertia is 880 kilogram meters squared. Omega 1 initial is 20 RPM. John is object 2. He is running at 5 meters per second, tangent to the merry-go-round, and jumps on the outer edge. All right, so if I was looking down from above and I said this merry-go-round was rotating counterclockwise, John is running tangent, so right next to the disc, and really he would be right here, running just as he jumped on. Because R and P, his momentum, are perpendicular, we can consider John as having angular momentum of R cross P. Now, this equation, R cross P, as we mentioned in an earlier video, it assumes the mass is concentrated at one distance r from the rotation axis. But it tells us to treat John as a point mass, so that is the assumption and approximation we're making. So because this is a cross product equation, the R and the P, it's only the components that are perpendicular to each other that are contributing to the angular momentum. So the fact that they're telling us that he's running tangent to the merry-go-round is important, because they're telling us that these are essentially perpendicular. And so John's momentum, angular momentum, will simply be R, that how far he is from the rotation axis, times P, his linear momentum. So RMV. This angle phi is 90 degrees, sine of 90 is 1. So ultimately, we're saying both the merry-go-round and John have angular momentum initially. And that will still be angular momentum of the system as a whole finally. Okay, this equation over here is specific to a point mass. That's why we can use that for John. The equation that always works for all objects is I times omega. We can use that for the merry-go-round. We could also use it for John. For John, the I would be mr squared. Omega would be v over r. This becomes RMV. So it simplifies down to the same thing. So this would be I omega. It simplifies down to RMV when we're trading anything as a point mass. All right, so object 1 is the merry-go-round. Object 2 is John. So over here in my equation, I can say I1 omega 1 initial plus RM2V2 for John. That still needs to be angular momentum finally, since they are both rotating together finally. I can factor out the omega final, and that gives me I1 plus I2 times omega final. Okay, unit-wise, for the previous example problems, we've been able to leave omega initial or omega final in terms of the revolutions per minute or revolutions per second. That is not the case here. And that's because this term, R is in meters, mass is in kilograms, V is in meters per second, the radians are implied in this. This is kilogram meter squared over seconds. The radians are implied within this, meaning both I1 omega 1 initial and this combination times omega final, the I's are in kilogram meters squared. Omega must be in radians per second in order to add these terms together, because we can only add terms that have like units. So we do need to convert. Technically, we could leave John in terms of ion omega and convert his omega to revolutions per minute if we wanted. That would be fine. Or we end up converting initially our 20 revolutions per minute to radians per second, which that's what I'm going to do. So coming up to our omega initial, we know we have 20 revolutions per minute. To convert, we know that 1 revolution is 2 pi radians. That will get rid of our revolutions. 1 minute is 60 seconds, so that's going to get rid of our minutes. Let's see, 20 goes into 60 3 times. So 2 pi over 3 radians per second is omega 1 initial. So now, having proper units, our omega final will end up being in radians per second, which we'll need to convert back to revolutions per minute, because that's what this problem is specifically asking for, which is fine. So I1 was given 880 kilogram meters squared. Omega 1 we have in radians per second. R, in order for John to jump on the merry-go-round, he's got to be right immediately next to it. So I'm going to go ahead and say he is that 1.5 meters away immediately before he jumps on. His mass is 30 kilograms. He's running at 5 meters per second. So that will be the angular momentum of John right before he jumps on. So 880 for I1. I2, so I2, again, a point mass is a hoop essentially. Well, it's not a hoop. It's the same equation as a hoop, I should say. The mass is concentrated a distance of r away, so I is mr squared for a point mass. So mr squared omega final. So let me plug these numbers in. I'm getting 2.183, but this again is in radians per second. We converted omega 1 initial to radians per second. The R and V, the radians, are implied. So we do need to convert back. So 2 pi radians in a revolution, and then 60 seconds in a minute. Make sure my seconds cancel. So getting this back to RPM, I'm going to multiply by 60 and divide by 2 pi. Make sure you have parentheses when you're dividing by 2 pi. I'm getting 21 RPM because I'm getting revolutions per minute. So it is traveling faster than it was before because John was running in the same direction. He had angular momentum, which was part of the system, and so together they now are rotating a little bit faster than the merry-go-round was rotating originally. If you're ever wondering about units, so the last couple problems we left omega in revolutions per second or revolutions per minute. If you're unsure, just convert to radians per second to be safe. And then you can convert back after the fact, if need be. If the problem doesn't ask for specific units for your answer, then any units will work. Radians per second would be perfectly valid. This particular problem specifically asked for that final velocity in angular velocity in RPM, and that's why I needed to convert back.